introduce you to the idea of linear programming, the technique of linear programming, which is a type of mathematical programming technique, and we'll do a few examples based on linear programming this week. So, linear programming is a way of mathematically formalizing the decision-making process. So if you look at the decision-making process itself, every decision that is made in the business, you say in the business context, but it could be any context at all. It has three elements to it. The first is usually a big decision involves a set of smaller individual decisions, and all of these decisions are being taken to usually achieve a single or sometimes multiple but related objectives, and this is done while you're subject to constraints. There's always constraints in real life scenarios. So think of any decision that you've made. There are lots of decisions that would have profoundly affected your life. Where did you go to college? What type of car to buy? What type of major to pursue? What type of job to get? There are lots of decisions that you might have made, and each time you made a decision, your decision involved all of these three elements: a set of smaller individual decisions used to achieve a single objective while being subject to constraints. And the idea of mathematical programming is to, like I said before, formalize this procedure and mathematically formulate it so that you can solve the problem as a math problem, get a solution to the math problem, and then interpret that solution in the context of whatever real life problem you're pursuing. So decisions, the set of individual smaller decisions in mathematical programming are represented as variables. We'll call them decision variables. The objective, usually in real life problems there might be multiple objectives, but in mathematical programming we always consider a single objective. So even in real life problems you might have multiple objectives, but there's always one that is more important than all the other ones, and that's the objective, the main objective. And that objective is represented as a function called the objective function. And finally, the constraints will be represented as equations and inequalities. And that's the mathematical programming technique, which is to formalize the general decision-making process. So a linear programming is a special kind of mathematical programming technique where all your the constraints and the objective function, they are all linear. And usually the objective will be to maximize or minimize something, and in most business contexts it will boil down to maximizing profits or minimizing costs. But in any linear programming problem, the objective is either to maximize some the objective function or to minimize the value of the objective function. And the constraints are like I said, they have to be linear in linear programming. Now, a feasible solution is a solution that satisfies all the problem's constraints, but the optimal solution is one that results in the best value. So if you're maximizing, it has to be the largest value of the objective function. That's the solution that gives you the maximum value of the objective function. And if you're minimizing, that is the solution that gives you the minimum value of the objective function. Now, a graphical solution method is a method that you can use to solve linear programs with two variables, but we are not going to go through the graphical solution method. We will mostly be using Excel as our solution methodology. Now, solving linear programming problems involves two major steps. The first step is called problem formulation. So after I go through this set of slides, I'll be posting this video. I'll be posting a few more videos, a couple of more examples. So there I'll be posting separate videos for problem formulation and then for problem solutions. So problem formulation is the process of translating the verbal statement into a mathematical statement. And formulating involves coming up with the decision variables, coming up with the objective function, and the constraints. So the guidelines for model formulation usually are these. So you have to first understand the problem thoroughly. You cannot miss or skip any part of the problem. You have to describe the objective and constraint. And then once you've understood the objective and the constraint and you're very sure about the descriptions, you start by defining a good set of decision variables. Now, based on the context of the problem, the decision variables will sometimes be pretty straightforward. Sometimes they might involve some hidden account keeping sort of decision variables. So if you're doing some sort of production planning, you might have a decision variable that keeps track of how much inventory you have on hand, that sort of thing. So you have to define a good set of decision variables, and then using the decision variables you come up with the objective, and also using the decision variables you write the constraints. So like I said, the decisions are variables, objective is a function, and constraints are equations and inequalities. So what we'll do is we'll take an example. This is a simple example. I'll go over this example in this video. After we go through the example, I will also solve the problem in Excel to show you what the solution methodology looks like. And then after that, I will post a few more videos of me solving a couple more examples. So this is a simple example of a furniture company that produces inexpensive tables and chairs. There are no colors on it, there are no special additions on it. It's just simple chairs and simple tables. And the manufacture of these tables and chairs involves two departments, a carpentry department and a painting department. So chair is more intricate to make than a table. A table is just a slab of wood with four legs, but a chair has a lot of intricate joints and stuff. So a chair requires more time in the carpentry shop, in the carpentry department, while because the table is larger, it requires more time in the painting department. So each table takes 3 hours of carpentry work and requires 2 hours of painting work, while each chair requires 4 hours of carpentry work and 1 hour of painting work. Now this is interesting. So you'll notice that the total time required to make a chair is 5 hours, and the total time required to make a table is also 5 hours. But you need more and less of carpentry and painting for each of that. Now, the company has 60 carpenters and 25 painters, each of whom can work 40 hours a week. So each of the 60 carpenters and each of the 25 painters can work 40 hours a week. And based on profit margins, the company knows that each table sold results in a profit of $7, while each chair sold results in a profit of $5. So the question is, based on these constraints we have on time, how many tables and how many chairs should we be making so that we maximize our profit? And that's the problem that we'll be solving. So we are going to formulate the problem as a linear program, and then we will solve it. All right? Okay. So like I said, there are 3 steps to formulation. So you have decisions, then your objective and constraint. So step 1 are the decisions and the decision variables. So the solution of the problem should tell us how many chairs and how many tables the company should manufacture per week. So the final solution will tell us the number of tables and the number of chairs that are made per week, and that is what your decision variables are. So you have one decision variable T, which is the number of tables that you make per week. You have another decision variable C, which is the number of chairs that you make per week. So these are the 2 decision variables that you have. Now using these 2 decision variables, now let's define the objective. Now the objective here is pretty straightforward. We want to maximize the profit that we make. So the objective function will be, so remember, each table gives you a profit of $7, while each chair gives you a profit of $5. So the profit function can be represented as 7 times the number of tables that are made, that is T, plus 5 times the number of chairs that are made, which is C. Now, at this point, it's very easy to fall into the trap of trying to figure out what the solution is. Now, the thing about linear programming or mathematical programming problems is that you formulate the problem using the variables that you've defined. At this point, do not worry about what the solution is going to look like or trying to do something that will give you a certain solution. Just come up with an objective, come up with a set of constraints based on the data, and let the solution be what the solution is. Right, now for the constraints. Step 3 is the constraints. There are two constraints in this problem. The first constraint is the carpentry time constraint, and the second constraint is the painting time constraint. So the carpentry time constraint is the total time required to make tea tables and C chairs cannot exceed the total labor time that's available from all the carpenters, which is so it will be 3 times T, because each table requires 3 hours of carpentry, plus 4 times C, because each chair requires 4 hours of carpentry. So 3T plus 4C is less than or equal to the total time available from all the carpenters, which will be 60 times 40, 40 hours a week, and the 60 carpenters. So that gives us 2400. Similarly, the painting time constraint is the total time required for painting all the tables and chairs cannot exceed the time that's available, which is 25 painters times the 40 hours a week each of them work. That's 1000 hours. So each table requires 2 hours of painting, so it's 2 times T, and each chair requires 1 hour of painting, so it's 1 times C. So 2 times T plus 1 times C is less than or equal to 1000. Right? So those are the two constraints, and we can represent them as a linear programming problem this way, where you say the problem is to maximize 7T plus 5C subject to the two constraints 3T plus 4C is less than or equal to 2400 and 2T plus C is less than or equal to 1000. Now, these are the two main constraints, but apart from this, we also have two other technical constraints to think of. The first one is non-negativity. So we say non-negativity because both of the variables, T for tables and C for chairs, both of these variables can either be 0 or they can be positive. So because they are not just positive, we say non-negative. So that's the constraint, saying that they can either be 0 or positive. And also the number of tables and the number of chairs have to be integer values, have to be whole number values. They have to be either 1 or 2 or 3 or 4 or maybe even 0, but they have to be whole number values. They can't be 1.5 or 2.5 or 2.25 or some number like that. That doesn't make sense. So technically speaking, we have to impose an integer constraint, but once you impose an integer constraint, the problem becomes so much more difficult to solve. So what we are going to do is we are going to ignore the integer constraint completely and then hope like hell that the solution actually turns out to be an integer. Now in this case, the solution does turn out to be an integer because of the way the coefficients work out, but it's not always the case. But the first step is always to ignore integer constraints and solve the problem and see if the solution automatically is an integer or not. In many cases it is, in some cases it's not, in which case you have to impose the integer constraint, and then the problem becomes much more difficult to solve. Right? So we will be solving this problem with the graphical method and with Excel. So we'll first look at the graphical method next week and with Excel the week after. Right. Take care.